Today we're going to do linearizations of functions, and the idea of a linearization is this. If you have a curve, like so, and you're trying to evaluate a curve, it usually involves some high power functions, or it could have a radical curve. Maybe it does like some cube root or square root function does something like that, and you're trying to evaluate something like that. And the idea of linearization is that as we get really close to a specific point on that curve, what's up? Yes. Okay, as we get really, really close to the point on the curve, let's say I'm picking this point right here, and I want to evaluate that specific value on the curve. If I look really close around that point, even if it's a curve, really close to that point looks like a straight line, right? Specifically, if I were to make a tangent line to this curve here, specifically, through that point, let's try and do that. Let's see, that's pretty close. That's pretty good. All right, and I really look at that in a zoomed in mode. The black line is the tangent line, the blue line is the curve. They're almost exactly the same, right? So the idea of linearization is if we can create some linear function that approximates the function near the value we care about, we can then use that linear function to evaluate. That's very easy to do. All right, 1/2 times 2 plus 1 instead of the square root of something, or the cube root of something like that. So that's the idea of this linearization idea. And here's the specific procedure, what you have to do. This is the formula right here. L of x is the linearization of the function. F of a is the function's value at x equals a. And f prime of a times x minus a. So a is what they're going to give us. X is the letter x. F of a and f prime of a both have specific values. All right? And then that allows us to find the answer near values of a. So if I have a equals 2, as long as I'm within a specific range, I can get a pretty decent approximation by the tangent line, basically, to evaluate the function itself. All right, does that make sense? As far as what we want to do? Find the derivative, evaluate both the function and its derivative at the value, write the linearization using the formula, and then simplify the expression completely. I'm going to have that up side by side here while I do this one, so we can just kind of go step by step through. So, example 1, find the linearization of the function f of x equals 1 over the square root of 4 minus x at a equals 0. And use it to approximate the numbers 1 over the square root of 3.87 and 1 over the square root of 4.01. All right. 1 over the square root of 3.87 would be x equals 0.13, right? Because 4 minus 0.13 makes 3.87. Right? Mm-hmm. And 1 over the square root of 4.01 would be x equals negative 0.01. Because 4 minus negative 0.01 is equal to 4.01, right? And I think we'll all agree that both those numbers are somewhat near to 0, right? Obviously, negative 0.01 much closer to 0 than 0.13, which means the approximation for this should be much closer than that. All right? Step 1, find f prime of x. So f of x, I'll do a full page here while I do it, and then I'll come back. So if I look at f of x, do I want to differentiate f of x the current way it looks? No, not at all. It's a radical, it's a fraction. Okay, first of all, the radical, we can obviously deal with that, that's half power. That's easy, right? 1 over 4 minus x to that 1/2 power. That is equivalent to that. I haven't done any calculus yet, so I'm continuing to call it f of x. Is that the best way to go? Can I do it this way?
You could.
Quotient rule, I could. Is there any way to make it any prettier? I can put it on top. Since it's just a number on top, changing it to the quantity 4 minus x to the negative half power is legal and easier. Now we're just doing a chain rule. Where here I have to do the quotient rule mixed with the chain rule. Okay, here I'm doing the chain rule mixed with the power rule. Power rule is easy, quotient rule is a little bit more challenging. They'll both get you the same answer. But I want you to start recognizing when you can make things easier. So number over function of x, do the negative power, and then you have a power function instead of a quotient. If it was x over this, maybe quotient rule fine. Because the best you can do is put an x there, now you got to do a product rule. Take your pick which one you like better. Quotient rule, product rule, doesn't matter to me. Okay. But again, as long as you're doing legal algebra, you can modify the structure to make it into something else. This is much easier to differentiate from that. So, f prime of x is going to equal -1/2 times 4 minus x to the -3/2 times -1. Again, it's a power function to start off with, so I did the power rule. Power times base to 1 lesser power, and then the derivative of the argument is -1. If I simplify it all, make it as pretty as I possibly can, f prime of x equals, I'm going to get +1 on top, and 2 times 4 minus x to the 3/2 on the bottom. That's my first derivative. And that's all step 1 is. Find the derivative. Step 2, going back full page or 2 pages. Step 2, we want to find f of a and f prime of a. Okay, so f of a is equal to what?
0.
There, a equals 0. F of 0 equals something, and f prime of 0 equals something. So f of 0 is this function. We're going to get 1 over the square root of 4. What does that equal? 1/2. Very good. And then f prime of 0 is 1 over 2 times 4 to the 3/2 power. What does that equal?
1 over 8 to the 3/2.
Not 1 over 8 to the 3/2. That's multiplying before you take a power. You got to do 4 to the 3/2 first, then multiply by 2. 3/2 power means take the square root of 4, which is?
1 over 12.
Square root of 4 is 2, and then 2 cubed is? 8, and 8 times 2 is? 16. We are in calculus. Remind you guys this. We learned that in Algebra 2. About, I don't know, October, Algebra 2. So you had all the rest of Algebra 2, all of geotrig, and now a couple of months of calculus to know how to do this. To take a fractional power of a number that has a nice pretty root like 4, 4 to the 3/2 power, that's the square root of 4 cubed, and the square root of 4 is 2, cubed is 8. That should be child's play, you guys. Okay, when you learn something in math, you need to practice it, master it, get good at it till you're able to do it just in your sleep. Okay? Fractional power, the bottom number is a root, take the root of the number, the top number is a power, you take the power of the number. 4 to the 3/2 is not a hard problem. Any number to some fractional power, at least in the case of these problems here, for the most part, are going to be friendly like that. If it was like 7 to the 2/3 power, use a calculator, because there's no cube root of 7, right? If it's 8 to the 2/3 power, now you should equal 4, because the cube root of 8 is 2 times itself is 4. That's what a fractional power is. Take the root, take the power, there's your answer. So, square root of 4 is 2, 2 cubed is 8, times 2 is 16. The 1/16 is what we get out of that. Alright? So that's what step 2 is. Evaluate the function at A, evaluate the derivative at A. Alright? So these two numbers are important to us. Step 3, going back here. Oops, maybe going back here. There we go. Write the linearization, use the formula. The formula says L of x is equal to f of A plus f prime of A times x minus A. That's the linearization formula. So if I come back over here, got my formula right there. F of A is 1/2. F prime of A is 1/16. And A equals 0. Alright, so if I just substitute stuff in, I get L of x is equal to 1/2 plus 1/16 times x minus 0. And if I beautify that up, it just becomes L of x equals 1/16 x plus 1/2. Step 4 was simplify. Simplify the expression. There we go. Yeah. Alright. So just like that, we got the linearization formula here. L of x equals 1/16 x plus 1/2. That is also the slope of the tangent. That's the equation of the tangent line. It's a different way to find the equation of the tangent line. So anytime they ask you for the linearization of a form function, they're basically asking for the equation of the tangent line. That's just kind of a systematic process to do it. Alright, so L of x equals that. Now, real quick, let's just take a look at this function, y equals, clear. If I do 1 divided by the square root of 4 minus x, and I do 1/16 x plus a half, x over 16 plus a half. So as far as window is concerned, I know that x has to be less than or equal to, or just less than 4, right? Can't divide by 0, so it's got to be less than 4. If x equals 4, you get 0, you can't divide by 0. If x is less than 4, 4 minus a number less than 4 is going to be positive. So let's go from -2 up to 4. And I don't know, let's go from -10 to 10. Let's just pretend we don't have any idea what's going to happen here. Hit graph, see what happens. There's 1 over the square root of 4 minus x. And there's 1/16 x plus 1/2. Really close to each other, right? Specifically here at 0, they're exactly the same thing for a while, it looks like. So if we focus in on that, let's just go from -1 to 1. And let's go from 0 up to 3. Now let's go to 2. Doesn't look very big. Big graph, see what happens. All right, there's my function, 1 over the square root of 4 minus x. And there is my tangent line. Look almost identical, right? And that's the whole idea of linearization. That tangent line is so close to the function that they're pretty close. They're pretty much the same thing. If I got in a lot closer, let's go from, let's say, 0.4 to 0.6. I know 0.5 is, we're 0.5, right? So 0.4 to 0.6 is above and below. There's the function. See that curve to it. And there's my line. Now you can start to see a little discrepancy there. As we zoom in really close, we can start seeing that there's like this little discrepancy. Where's my line in relationship to the curve?
It's below it.
Below it. It's underneath it, right? Which means that my curve is an underestimate. All right? And that's one of the questions they're going to ask you a lot of times on these is, are the approximations that we're going to get, are they going to be underestimates or overestimates? So if my curve is here and my slope is there, it's an underestimate. If my curve is here and my slope is there, or my equation tangent line is there, it's going to be an overestimate. So that's how you tell the answer to the question, approximates over or underestimates. All right? As far as evaluating 1 over the square root of 3.87 and 1 over the square root of 4.01, let x equal this, let x equal that into this function, and you can approximate. Again, that's what we're approximating, right? So if I do L of 0.13, so again, for 1 over the square root of 3.87, x equals 1.13. This is my linearization. There's my approximate area, right? Or line value. L of x equals this. It's going to equal 1/16 times 0.13 plus a half. Okay. That's not any real easier to do than, oh, let's see. This would be 13 over 1600, right?
Mm-hmm.
0.13 over 16, move both decimal places, 2 spaces, 13 over 1600. 1/2 is the same as 800 over 1600. So that's going to equal 813 1600ths. There's my approximate value for the square root of, or 1 over the square root of 3.87, 813 1600ths. If we look at L of -0.01, so I'm approximating 1 over the square root of 4.01, L of -0.01, that's going to be 1/16 times -0.01 plus 1/2. That's going to be -1 over 1600. This is 800 over 1600. That makes 799 1600ths. Let's just try these out real quick. So, those are my approximations. If I do 813 divided by 1600, comes out to that decimal. If I do 1 divided by the square root of 3.87, 0.508125, 0.508329, they're almost the same. And again, I didn't use a calculator to do that. I'm pretty good at fractions, you guys are too, so that should be doable for you. If we look at the other one, if I do 1 divided by the square root of 4.01, that comes out to 0.499376. If I do 799 divided by 1600, that comes out to 0.499375. Okay, so 5 decimal places the same, the 6th one is where it changes. Notice that's a lot closer, because negative 0.01 is a lot closer than the 0.13 was. The closer you are to the actual value of A, the closer your approximation is going to be. All right? So that's what I'm looking for on this. I want to see your linearization. I want to see you apply it. Give me a fraction answer. I don't want you to use a calculator on this part. So if it comes down to making fractions out of it, so be it. But if you can evaluate it down to a nice pretty number too, that's fine too. But that's what I'm looking for, is to use the approximation to get an answer without using a calculator. Use the calculator along with the graphing function to establish the fact that underestimates or overestimates. In this case, these are underestimates, because the tangent line is underneath the curve. So the tangent line is what we're evaluating, the curve is what they actually are. So we're below it, so it's an underestimate.